Okay, and up next in our last presentation before the discussion section, we have Francesca McDonald. Francesca, are you there?
Yes, I'm here.
Hey, thank you.
Lovely. Thank you for giving me the opportunity to speak. Good evening. So I'll be providing some inputs on behalf of ESA and its interactions with the European science community. Next slide, please. So just to iterate here that Europe has been very much involved with sample science right from those very first returned samples during the Apollo era from Apollo 11. There's a strong contingency and a lot of expertise in Europe working very well in international collaboration with America and the rest of the world. And a few statistics there, I'm sure Ryan and Juliana might correct me, but on average, you do have around about 35% of these samples going to PIs in European institutes. So there is a strong history there, and this is continuing to the next generation. And also, Artemis, there's already a deep involvement from ESA, where there's already contribution from the European Service Module for Orion, Gateway collaboration, and already talking of cooperation on the CLIPS robotics activities, so very much involved already. And we already have the ESA strategy for science at the moon that's very much aligns with those well-identified outstanding science questions of the international lunar community. Well, what's going to be prime is really understanding what's the key when it comes to lunar South Pole as a prime target. Non-PKT terrains are going to be a prime place to explore, but certainly the lunar South Pole is going to be up there. And this drives many questions when it comes to integrating into sort of the engineering systems that are also required. Next slide, please. There's been lots of these themes throughout the day, so it's great to see we're all marching to the same tune. So, but if we're going to be considering that icy or volatile-rich samples at the poles is at the forefront there, then there's a lot that needs to be considered. Your types, masses, numbers, and diversity of samples you can collect may all be affected if you're going to be including these icy samples. It's going to be a function of what analytical techniques are going to be used, what sensitivity is required, and also being driven by those science questions. So here we've done these polar sample return mission studies in the past, and these were the key areas that really need further investigation. It sounds like there's some good work already going on in this area as well. So how do you acquire these samples? Where will we be accidentally introducing any contaminants, and how do you monitor and account for this? And then this case of having a sealed versus how you cryogenically preserve, that's a lot of demand on payload mass and effort and astronaut time. There's other options that can be considered. Is perhaps evolving the gas prior to capture and containment an approach that could be one to be taken depending on what your science questions are. It could be that there is not a one-size-fits-all approach for these icy samples, but it's going to be very important to do detailed trade studies identifying what is required for the sample science curation versus what is the engineering capability versus that optimum sample return mass that you're looking for. As I said, it's really looking into that science and the payoff, and working in line with the sample questions and with the curation. Next slide, please. But there are other aspects there are other approaches you can take to also help with this, and that's how can we use robotic missions to support the Artemis, whether it's in the sample planning or at the sample return itself. So work has started at ESA for a European large logistic lander, and this can deliver cargo or robotic systems capability to the lunar surface, which can be coordinated to support Artemis. So we're really looking to question sort of which robotic measurements can support identification or maybe priority sites or samples for crewed sample return. What geological context measurements will be useful? It's really about optimizing sample selection and collection, optimization of astronaut time, and guiding the context of what type of sampling and approach you'd use. Perhaps these measurements could be used to be looking at the physical and geotechnical properties of the soils and the regoliths. Perhaps it could be looking at how dust interacts with these new technologies and tools that are being developed. Perhaps it could be even investigating regions of varying ice stability depth, or getting a bit more of a reconnaissance over an aerially spatial area to really sort of start refining down where you go for your samples and how you support that selection. Maybe sample caching is another thing that could be considered. Next slide, please. And we've heard it enough times before. Of course, the most valuable tool of all is the astronaut, and we have the ongoing ESA Pangerian Caves training program providing such vital astronaut training and doing this new field tool development testing as well. We heard Judy talking about how you need to adapt these tools to the questions as well. And this field analytical kit that is being designed at ESA At the hub of it is electronic field book. It's a kind of smart tool for integrating the crew with the ground support and science backroom. It includes a planetary mineral database that's been derived from archives of multiple spectra, including Raman, VNIR, XRF, and LIBS. There's also surface imagery packages there. There's real surface context and geological context. And all of this can help optimize the effectiveness of the crew in the field, support recording sample geological context, and assisting with returning sample prioritization. Next slide. So that just to finalize here, it's going to be the key is this robotic and human crewed partnership moving forward. Thank you.